Hello, today I'll be talking about Russian constructivism in a pre-fascist theory. So our object of study will be CIC, the calculus of inductive constructions, which depending on your background you can see either as a very fancy intuitionistic logical system that has a built-in notion of computation, or as a very powerful functional programming language that is equipped with proof features that allows to prove your programs correct. And this is why I call CIC the pinnacle of the Curry-Howard correspondence. And if you need to picture that system more faithfully, you can just imagine the Coq proof assistant. So what we want to do is to extend CIC with new reasoning or programming principles. And for that, we actually need to design models and ensure that they further satisfy what I call the good properties that include, for instance, consistency, canonicity, decidability of type checking, or strong normalization. The kind of models we will study today are Presheaves, a very specific family. They are used virtually everywhere for a lot of different constructions, so they are really pervasive, and you can consider them as some kind of proof-relevant cryptic semantics or also intuitionistic forcing. So let us fix a base category P. A Presheave over P is simply a functor from P up to set. So Presheaves with natural transformations as morphisms actually form a category. And if we unfold the definition, that a Presheave is essentially a pair of a family of P-index set AP together with what are called restriction morphisms, that is functions that, given a proof that Q is smaller than P, produce a function from AP to AQ that furthermore satisfy functional equations. And a morphism from A to B is no more than a family of P-indexed functions FP from AP to BP that are natural in P. And I won't have much time to discuss it, but actually Presheaves form a model of CIC. So we can look at the properties we like in this model. So there is no proof of false in Presheaves, which is good. That means that the model is consistent. If you pick a closed integer in the model, that implies in set theory that this integer is actually a real integer. But this is kind of suspicious because depending on the exact meta theory you're living in, this means different things. If you pick classical set theory, then that doesn't mean much, but the Presheave construction is amenable to be expressed in constructive set theory, in which case you can actually construct a real integer. Because sets are blobs, it means that you don't have decidable type checking. You have the full power of ZF, so you can't decide anything. And worse, there is no way to speak about reduction because there is not even syntax to start with. So strong normalization is completely out of the window. This is the reason why I usually claim that models that are based on set theory really suck. Instead, we advocate for another kind of models that are called syntactic models. And the idea is that a syntactic model is no more than a compilation phase. The idea is you have to define a single bracket and double bracket translation that are defined by induction over the syntax. And what you want to get is the fact that if you have a term M of type A in the source theory, then actually through the translation you get a translated term that has type, the translated type in the target theory. And what we hope is that the target theory is somehow bigger than the source theory. Syntactic models are pretty hard to come up with, but they are kind of strong in the sense that they do not require anything non-type theoretical. You don't have to use set theory or anything. You can implement them very straightforwardly in Coq by merely writing a compilation phase. And because they put syntax on the foreground, they actually automatically inherit all the good properties of CIC for free. There is nothing to be done specifically. The question we'll be interested with today is whether it is possible to see Presheaves as a syntactic model. And the reason for that is that there have been 3 atoms in this line of work, and this is the 3rd atom that I'm presenting today. And the 2 previous ones from 2012 and 2016 were kind of failures. And I'm going to come back on that right now. So let's review the 2012 atoms. So this just stems from saying that a Presheave is a functor from P up to set. So it's very easy to get a type theoretical equivalent. You just replace set everywhere with CIC. So you say that a category is just a type P together with a type of morphisms that is equipped with an identity, a composition, and that furthermore satisfy a few equational properties about composition. Then you say that a Presheave is a type that is made out of an index type A, restriction morphisms, and further equational theories. And the thing is that this kind of works, except that no, because you have you have propositional equations on these fields in the equational properties, which implies that you don't preserve conversion via this interpretation. That means that if you have 2 terms M and N that are convertible in CIC, then they are not necessarily convertible in the target theory. You merely get a proof E that M and N, or their translations, are equal propositionally, which means in turn that you need to introduce rewriting everywhere using those equations. This is very well known as the coherence hell, and the only way out is to require the target theory to be extensional, in the sense that to prove M is convertible to N, it is enough to invent a proof E that M is equal to N out of thin air. This is kind of better than ZFC because you get some kind of constructive flavor, but clearly this has undecidable type checking because you need to invent proofs, so this is undecidable. But furthermore, computation is completely destroyed. Even deciding merely whether you are able to reduce beta reduction is not possible. And I recommend reading Theo Winterhalter's PhD thesis for more horrors about this theory. Therefore, I believe that this lack of computational content means that entity is not really a type theory, and by definition of a syntactic model, that means that we don't really have a syntactic model for Presheaves. Let's look at the 2016 version. So the key observation is that Presheaves actually factorize through a call by push value encoding via a call by value decomposition, which implies that the only definitional equation that is satisfied is the call by value 1, which means that the beta reduction is restricted to values. You can only reduce a beta reduction whenever the argument is a value. But meanwhile, type theory is clearly called by name, in the sense that the conversion rule says that you can replace A by B in the right-hand side of a column whenever A is convertible to B for the beta equational theory. And unfortunately, it's very well known that CBV and CBN are not the same thing, which explains why it doesn't work. So because we have a call by push value decomposition, there is an easy fix, which is to pick the call by name decomposition instead. So how does it do? The call by value interpretation of an arrow says that A implies B at P is for all Q smaller than P, A at Q implies B at Q. Meanwhile, the call by name interpretation says that this is for all Q smaller than P, A at Q at the left hand side of the arrow implies B at P. So B didn't move along P, and the quantification has moved on the left hand side of the arrow. So in general, these call by name types are not interpreted as factors but merely index types. And we get factoriality by freely thinking over all lower conditions that you can see in the arrow. That is, we say that for all Q smaller than P, A at Q, this is freely thinking. And the good thing is that this interpretation goes straightforwardly to the dependently typed type theory. So we get a syntactic model of CC omega, which is CIC without inductive types, into CIC. But the problem is that the model disproves dependent termination, and in the sense that inductive types are have broken. Thus, we don't have a proper syntactic presheave model. Okay, so presheaves actually interpret full beta conversion, although extensionally. So why is that? Because there is an additional requirement on functions, that is naturality. We require morphisms to be natural in P. And we observed that this naturality corresponds to an agnostic notion of purity known as thinkability. And this is a systematic construction. Through that light, we can see the presheaves as the pure fragments of an effectful call-by-value language. So it's very well known that if you have effect in call-by-value, you break functions, and therefore substitution, you don't get full beta. But purely in call-by-name, these effects are breaking inductive types, and thus you don't get dependent elimination. So clearly we were missing the equivalent of naturality in the call-by-name presheaves, which is why we didn't get dependent elimination. And this equivalent is actually parametricity, and it turns out to be a syntactic model. So what does the parametricity look like on this presheave model? So it says essentially that if you have a variable x of type bool, you're going to interpret it as not one, but two variables. So first, the underlying effectful translation, x, that has type for all q smaller than p bool. And furthermore, a proof of parametricity, x epsilon, that says that x is parametric as a boolean at p. And if we want to get dependent elimination, we need that this parametric predicate implies that x is constantly true or constantly false to ensure that it cannot observe the effects. And furthermore, because this x epsilon is used throughout the proof by all the terms, this needs to be done in a unique way in the sense that bool epsilon needs to be a hot proposition. But at the same time, this has presheave structure, so we need to be compatible with the ambient presheave structure. So in particular, we need restriction morphisms for the parametricity predicate, saying that if q is smaller than p, then actually x realizes bool at p implies that the lowering of x at q is also a realizer at q. And furthermore, we need definitional equations to ensure that we don't get into the other coherence issues. And the problem is that you cannot have both things at the same time in CIC. And this is somehow the call-by-value versus call-by-name conundrum that has been raised one level higher, in the sense that instead of having it on the proof terms, we now have them on the realizability terms. So we were blocked on that when suddenly there was a paper called Definitional Proof of Relevance without K that was published at POPL last year. And this paper introduced a new sort S-prop of strict propositions, such that whenever two terms live in a strict proposition, they are actually convertible. And you can see this strict proposition sort as some kind of well-behaved subset of prop compatible with the hot that satisfies all the good syntactic properties. Importantly, S-prop is closed in the product in the sense that if you have B that depends on A, which is a strict proposition, then for all x and A at B is still a strict proposition. And dually, the only inductive type that you can eliminate from S-prop into type is in the end falsity. So this is stricter than the standard prop elimination. The authors discuss an extension that we will call SCIC for strict CIC that also, in addition to falsity, allows the elimination of equality from its prop to type. And this theory gives rise to what is called a strict equality, in the sense that strict CIC has definitional unicity of identity proofs. And this is in stark contrast with the libertarian hot approach, which freely adds these infinite towers of equality. Instead, strict CIC is authoritarian and will guillotine all higher equalities. So the major claim is that there is only one way to be equal. And this turns out to be the authoritarian way to solve the coherence hell. Thanks to strict propositions with UIP, we can fix the parametric presheave translation. So how do we do that? We make the parametricity predicate free by quantifying over all smaller conditions so that we get definitional functionality. But at the same time, we require it to be a strict proposition which will enforce proof uniqueness automatically. So that means that if I have in the source x of type A, then I get the same x as before, the underlying translation, plus the parameter predicate that says that for all q smaller than p, I realizes at q. And critically, the a epsilon is living in the strict proposition sort. This resulting translation, we call it the Prefascist translation, from Latin fascis, which means a sheaf. And this is actually a syntactic model of CIC that enjoys full conversion and full dependent elimination. This is really the idea that I've written both. And the use of UIP is critically required to prove that this theory has universes. Strict CIC is weaker than extensional type theory, so it is conjectured to enjoy the good properties. So canonicity seems in reach, but strong normalization is kind of problematic because it's known that if you add an implicative universe to strict CIC, then you're not strongly normalizing. But because we don't rely on implicativity for the prefascist model, we hope that strict CIC has these properties, and therefore the prefascist model would inherit them for free. Sets are a model of strict propositions, so in particular you can explain what the prefascist model is in sets. And you can really see them as a category that enjoy definitional laws. And if you look into the details, they really have a realizability flavor when you compare them to Presheaves. But the good thing is that as one category, Presheaves and prefascist sets are equivalent. So to prove that, you fundamentally require extensionality principles, but at the same time, prefascist sets are better behaved in intentional setting. So for higher category theory, this is clearly better. So somehow I claim that prefascist sets are a better presentation of Presheaves that is more compatible with intentionality. Let's look at an application now. So the Russian constructivist school is a variant of constructivism whose major belief is that all proofs are Kleene realizers. So in particular, they decree Markov principles, which is a principle that puts them apart both from Brewer style and Bishop style intuitionism. So Markov principle says that if you have a function f from nat to bool, and you know that not there exists a natural number n such that f of n is true, then actually there is a natural number such that f of n is true. And this is some classical property that stands in between, strictly in between intuitionistic and classical logic, but it is known to preserve what amounts to canonicity. And it is often required to prove various kind of completeness results. So what we want to do is to extend CIC with Markov principle via a syntactic model. So if we look at the realizer of Markov principle in Kleene Realizability, essentially this is an unbounded loop that tests f for every n starting from 0 upwards. And you need actually Markov principle in the meta theory to prove that this term realizes MP. So this is clearly cheating since the realizer doesn't use at all the doubly negative proof, and since it relies on having Turing complete language as realizer, there is no hope that you can get this as a syntactic model in CIC. So we need something else. Thankfully, there are not one but two alternatives. So the first one is Coquin-Hoffmann's syntactic model for HA omega plus MP. And the second one is a direct style proof by Herbelin that uses a weak form of delimited continuations. So you can see the Coquin-Hoffmann's model as a mix between cryptic semantics and Friedman's A translation. So the cryptic semantics is performed over a cell of type nat to bool, and being smaller in the cryptic model means to be pointwise truer. And the A translation is interestingly performed over a type of exceptions that depends on the value of the current cryptic cell. So A at P is there exists a natural number so that P of n is true. And the secret ingredient that makes the whole model work is precisely the fact that this type of exception is depending on the current cryptic cell. So this model is kind of ad hoc. So instead we're going to define a type theory called the calculus of constructions with completeness principles, CCCP for short, that is an extension of CIC, and that is defined as the composition between two syntactic interpretations. First, a prefascist model that we described before, and then an exceptional translation, which is the CIC equivalent of the A translation. And because this is done at such a high level, we get for free that if CIC enjoys the good properties, then so does CCCP. So very briefly, the exceptional model is a very simple syntactic model that essentially fix a type E of exceptions in the target theory, and you interpret a type A in the solve theory as both first a type together with a function from E to that type. So this function is a way to raise exceptions at the type. And in particular, if you look at the translation of negation, then this corresponds to the interpretation of the relativized negation at E. So now we're going to perform the exceptional translation over an exotic type of exceptions. So we're going to pick a type E that lives in the Prefascist theory. So how do we define it? We pick, as in Coq-Hoffmann's model, the Prefascist model over not-arrow bool, and we define, as they did, E at P as there exists a point such that P holds at the point. We also have a modality through a Prefascist model that we call local. So local says that if you pick a function from that tuple and a type, you can build a type of relativized types, knowing that there exists a point where this function holds. This modality is equipped with a few additional structure like return that says that A implies local phi A, and this modality commutes with arrows and positive types. And very interestingly, there is a property for local phi E that makes it commute with local, in the sense that this is isomorphic to either E or the fact that phi holds at some point. And you can then implement Markov's principle in that theory by merely performing symbol pushing in the middle theory and relying on the fact that the negation is interpreted as the implication relativized to E. If you look at the computational interpretation of this model, this essentially amounts to getting local exceptions, because local phi E is, as I said, either E or a function proof that there exists a point where the function phi is holding, so that it means that every time you go under local, you have new exceptions on your hands that come from this point truth. So you can really see return as some form of delimited continuation prompt. And if you look at Herbelin's proof, you very briefly realize that this follows the very same interpretation. And the try with block corresponds to the entrance to a local modality using the return combinator, and the raising really amounts to a raising in the exceptional model. In particular, you can see that the exceptions can escape from the P, which is reflected here by the fact that local phi E also might be some E. So actually, Herbelin's proof is really some direct style variant of Coq-Hoffmann. So to conclude, Presheaves are really a purified sublanguage of some kind of effect that corresponds to a monotonic reader. And we gave a better behaved presentation of Presheaves inside an intentional type theory. So it's equivalent as sets, but it is better intentionally. It is defined as a purely syntactic model, except that this model relies on having strict equality available in the target theory. So we hope that strict CIC enjoys the good properties, in which case this resulting model will enjoy all the good properties for free. For Markov principle, we can get this new principle in a type theory. This is a new result by a very simple composition of two models: the Prefascist model we described and the exceptional model that corresponds to A translation. And this is purely computational. that model satisfies all the good properties computationally, can extract programs out of it, and it validates MP. So what we would like to do with the new Presheave model is actually implement cubical type theory directly through this model, so that we can actually enjoy all the implementation and canonicity of CIC and COC via this interpretation. Thank you.